Hi, everybody.
Hello, Professor.
Hi. Sorry, 1 second. I'm just trying to get Notability to work. Okay. All right. Does anyone have any questions before we get started? All right. I'm gonna Christina is gonna start the lecture today. I'm gonna give a quick preview of where we're going before passing it over to Christina. Does that sound good, Christina?
Yeah, that's good.
Okay. And you're like pretty set with I see your iPad's also on, right? So you're gonna share your screen. Okay, you're all
Yeah.
cool.
Yeah, I hope it works. I had some trouble earlier today, but it should be good.
Well, I mean, we'll take the time to figure it out. I'm sure it'll be fine. Okay, so we've been seeing some nice things over the past few weeks, proving positive results. Like yesterday, we saw an especially nice result about the behavior of the structure of functions, of periodic functions in L2 in Hilbert space structure. Today, let me share my screen briefly, and then I'm going to pass it over to Christina. Today, the goal is going to be to prove the following proposition or theorem. I don't know what to call it, but it's an example. There exists a function f which is continuous on the circle, such that its Fourier series diverges at a point. So we're going to show that the goal is we're going to show that Fourier's original conjecture is false, namely that there's continuous functions with divergent Fourier series, and we're going to construct a particularly nasty continuous function during class. Okay, so that's the goal, and Christina is going to start us towards that goal. So I'm going to pass it over to you now, Christina.
Awesome. Oh, did my iPad just disappear? Oh no.
It did disappear. Take your time. There, I see it. It's coming back on now.
Okay. Great. Okay.
All right, this is looking good.
Awesome. Yeah, so we're going to see later a continuous function with a divergent Fourier series, but right now we're going to start with a discontinuous function which has a convergent Fourier series. So this is the function we're looking at. This is called the 2 pi periodic sawtooth function. And basically has these linear pieces, and then at 0, we want the value to be 0. And so I'm just going to write out what it is on, this is on the interval negative pi to pi, and then you just extend via periodicity. Oh, nothing's showing, is it?
We saw what you wrote, 2 pi periodic sawtooth function.
Oh no.
But then after that, I didn't see.
Okay. Hmm.
Okay. There we go.
Yeah. Okay.
F0, 2 pi periodic minus pi to pi.
Yeah. Oh, so that doesn't really say anything apart from F0. What it's supposed to be is F0 is 0. And Fx is negative pi over 2 minus x over 2 from negative pi to 0, pi over 2 minus x over 2 from 0 to pi.
Yeah.
Okay. And then naturally we'd want to talk about the Fourier series of f. So first we compute that for n equals 0. We get this from the definition.
Christina, it froze again, I think.
Oh boy. Okay. I'm on the MIT campus Wi-Fi. This shouldn't be happening.
Yeah.
Yeah, it's been like this all day.
Yeah, unfortunately, the MIT campus Wi-Fi sometimes is glitchy. Do you want to just do what you did before? Try again, like a log out, log in, or I mean, stop share, start share again.
Okay.
Don't panic. Last semester during the Zoom thing, I spent about 15 minutes trying to get my Apple Pencil, thinking my Apple Pencil stopped working. And someone finally had to tell me to try screwing in the cap a little bit more. Okay, so that was so. Okay, good. So you're writing out f of the f at the 0th Fourier coefficient 0. Okay. Sorry. Yeah. Okay, because it's odd, right?
Yep, it's just odd, and we can see from this. You can also compute it to verify, but I'm not going to do that right now.
Sure.
And then for n not equal to 0, so since it's defined in 2 pieces, we just want to integrate this in 2 pieces.
Oh no.
Dx. So it's gone again.
Huh.
So if I may interrupt, I've had this problem the last week or so. And I don't know if you've updated your software recently. That's when it stopped working for me. But what I do now is I connect my iPad to my laptop, and then I use the screen share, like share connected device.
That's what I do too. So do you have by any chance something that will plug your iPad directly into your laptop? Like it should just be like the iPad charger should be if it's a charger. Good, thank you, Augustine. That does seem that's often more stable. Good idea.
Or you can use cellular.
Sorry?
Do you want to use my iPad with it's got 3G or 4G or whatever it is?
Oh, okay. I guess I could do that too.
Do you have do you have your charger by any chance? Like
so I have this, but my computer doesn't have either of these.
Yeah. Thanks, Apple. Yeah. If you have wait, your AirPod, you have AirPods, right?
Yeah.
Did your AirPod charger come with a direct USB-C cable?
Oh, it's a different thing. Okay. Sorry about this, guys. I haven't had problems with this before. Sorry.
Yeah, there was something. So there was some problem with these. I saw something about this too with some software issue.
Okay, I think Andy is running over.
Okay.
I think that's what's happening. Hello. Okay. Oh my God, amazing. Okay. Join without video. Now we have Andy twice in the thing.
Gotcha. Thanks, Andy.
That's a very nice move.
Okay, and then share screen. And notability. Yes. Okay. Where were we? So, okay. So we have this function. Should I draw it out again, or should I just continue? We all sort of.
Yeah, just continue.
Okay.
Picture, unless the picture is helpful for anything, for you. Otherwise, I think we remember.
Okay, great. So n not equal to 0, then the Fourier coefficient is equal to 1 over 2 pi. And right, so we defined the function in 2 pieces. So this is how we want to integrate it. So this is pi over 2 minus x over 2 e to the negative ln x dx.
Yeah.
And then, so basically you do an integration by parts and you get a really big expression. But then it ends up just being 2i over n. Is that okay?
Mm-hmm.
All
so
right.
Integrate by parts, and then some things are going to cancel probably.
Yeah. Yeah, and then we just end up with this.
Okay.
So the Fourier series of fx is just going to be, we pull out the 1 over 2i to the front. And then when n not equal to 0, we're adding e to the I and x over n.
Okay.
Okay, so f is discontinuous, right? But we want to show that we have pointwise convergence of the Fourier series. So we're going to have a slight digression to talk about what the Dirichlet test is. And you can find this in the book. This is chapter 2, exercise 7. But basically what it says is if we have sequences, an being a real sequence and bn being complex, so n equals 1, 2, etc. Then if firstly the partial sums being less than equal to m for any n. So basically just boundedness. And also, number 2, we want the AN sequence to decrease monotonically to 0. And then if these two things are satisfied, then the sum AN BN converges. Okay, so we basically just want to apply this Dirichlet test to our partial sums. But I'm going to rewrite these partial sums in a more useful form. So what we already got is n not equal to 0, absolute value n small than equal to capital N of this. But actually we want n equals 1, 2, 3, etc. So n from 1 to capital N of 1 over n times e to the in x power, and subtract e to the negative in x power. And then sort of these two parts together should be reminiscent of the sine function, right? And then so we just have the sum. Okay. So in terms of our AN and BN sequences, we want this one to be AN and sine NX to be the BN sequence. And so to apply the test, I'm gonna look at the second condition first because that's easier to see, but basically just the sequence 1 over n decreases monotonically to 0. And that's good. We're happy with that. And then for the first thing, so this is just, we're just thinking about point-wise convergence here, right? So it's okay to think about for fixed x, and we want this x to be not equal to 2k pi. K is an integer. And we'll see why that is in just a second. But so if we take the absolute value of the partial sums, so these are sine nx's. So, you know, we can just write it out like this. And we're going to multiply the top and the bottom by 2 sine x over 2. Just, you know, the multiply by 1 trick. And we have this in the denominator, and then because x is not an even multiple of pi, we have the denominator being non-zero, which is nice. And then, okay, so the next step, I'm going to use the trig identity, which is that 2 sine alpha sine beta is equal to cosine alpha minus beta minus cosine alpha plus beta. And so basically just using this, I'll get cosine minus x over 2, x plus x over 2, 2x minus x over 2. And then eventually 2 cosine and x. And x plus x over 2 here. So that's the numerator. And so we'll get cancellation here, which is nice. So all these middle terms should cancel out, and then we just are left with 2. So I'll write it out again. Over q sine x over 2. And so the numerator is less than or equal to 2 just because it's the cosine function and the triangle inequality. So we get this upper bound, which is less than infinity. So yeah, for fixed x not equal to 2k pi.
Yeah.
Okay. And then, so we just deal with the remaining case, which is just that these partial sums, you're just adding zeros together because sine evaluates 0. Yeah, so we get, the Fourier series of this discontinuous function converging pointwise. And then what I want to say about the behavior of the Fourier series is that, so we have this sawtooth function, right? And then the Fourier series evaluates to 0 at 0, which is actually the average of these two guys here, which is nice, even though it's a point of discontinuity. Okay.
So in the proof you gave, you're in no way getting uniform convergence, right? And because it looks like like the bound is going to break down as you let x tend to these endpoints, right? Because x tends to 0.
Yeah. You could get uniform continuity if you just if you had a smaller interval.
Oh, good. Yeah. So it'd be if you fix the interval away from 0, like if you made a compact interval not containing 0, then you have uniform convergence there.
Yeah. But because we have 0, it doesn't work out. Yes.
Good.
Okay. Yeah. So we're building towards, seeing a continuous function with a diverging Fourier series. But a key idea with related to this is symmetry breaking. And symmetry here, we're talking about the symmetry between e to the in theta and e to the negative in theta terms in the Fourier series. So I guess I've sort of just switched to theta here, but basically just because we're defining these things on a circle now. And so examples would be like the partial sums. They sort of go from negative n to positive n, and you have that sort of symmetry. And then similarly with the Dirichlet, Thayer, and Poisson kernels, they're all sort of defined in this symmetric way. So let's see what happens when we break the symmetry, right? So just in a very general sense, if we have this Fourier series, and e to the in theta, and we break this into two pieces, So the non-negative n and the negative n, then well, the book says you get new and far-reaching phenomena, but we'll just see a simple example here. So let's say we have this g theta. So this is defined on the circle, right? And then we want this to be a 2i scaled version of the sawtooth function from earlier, just for convenience. And then the Fourier series should be just e to the I in theta over n. Yeah, we just scaled it to get rid of the constant in front, or yeah. And then on the other hand, we claim the following. So consider just the sum of the negative n terms. So unlike the above Fourier series, this is no longer the Fourier series of a Riemann integrable function, which is interesting. Okay, so the proof is not too bad. We're going to prove by contradiction. So suppose it is the Fourier series of an integrable function f tilde. And so in particular, integrable implies bounded. And we use the Abel means. You take the absolute value of the Abel mean when evaluated at 0. So just from the definition, we get this, so e to the 0 over n, absolute value. And then I'm going to flip it all over to positive n. And this is just Rn over n. And this actually diverges. It goes to infinity as R goes to 1, since the series summing 1 over n diverges. And there's like, you know, the proof using powers of 1/2 for that, but I'm not going to do that right here. So now we take this diverging thing, and it's actually less than equal to this integral. So here's the Poisson kernel, d theta. And this sort of just comes from how the Abel means is actually just the convolution with the Poisson kernel.
And then, yeah. And then
yeah, and then
0.
Yeah, exactly. And then we pulled the absolute values in, and the Poisson kernel is just always non-negative. So we have this. Yeah, and then this is less than equal to the sup over theta of the absolute value of f tilde, sort of because like the principle of convolving with these good kernels is that you're getting a weighted average. So it should be less than equal to the sup. And now we get a contradiction since implies f tilde not bounded. Yeah.
Okay, so yeah, so we have it's both bounded and not bounded, so that's a problem. Yeah. Okay, so this is pretty interesting. So I guess like so on the other hand, you just showed me before that the sawtooth function itself, like you can so the Fourier series associated to a sawtooth function is the Fourier series of a Riemann integrable function, and it's pointwise convergent. Can is it apparent where you use the symmetries and like that, and you proved that, right? You showed that very nicely. Is it like clear where you use the symmetries in the proof? The symmetry in the n and e to the minus n.
So I would think right. So right here,
yeah,
these guys combine to make sine of nx, but you wouldn't get that without the symmetry.
Yeah, and then yeah, yeah. So, but okay. On the other hand, if you this is interesting because on the other hand, I think if you just left e to the I n x there and just crossed out to e to the minus I n x, that still looks like it might converge to me. Just because e to the I n x by itself should oscillate a lot too, without it being sine.
Okay.
So I think it's really delicate. Like, I agree. That's what I was thinking too. Like exactly what your answer was is what I had in mind too. And now I'm wondering if it's like, because let's see. Yeah, I mean, okay.
Yeah.
And then going down, you showed all these cancellations, but then but it still looks like there's a problem. Oh, okay. So, on the other hand, what happens at okay, all right, now okay. So I think you're exactly right. So you showed that sine came up, right? And then you showed to be separately that at 0 there's no problem, right? Down below. So I think like if x is not 0, everything's okay. Like that thing still diverges. The series that you just still converges. The series still converges even if you didn't have a sign. But I think that sign was crucial for at the point x equals 0. Right? If you didn't have, if you go back up to that formula that you had.
This one?
Here, yeah. Because if I didn't like, if we just plug in x equals 0, if I didn't have the minus e to the minus I n x there, if I just had e to the I n x and I plug in x equals 0, then I'm in trouble, right? Because
because you're just summing like 1 over n.
Yeah. Yeah. So somehow this symmetry thing comes in here at that one point, at the point x equals 0. It's like it's crucial. It's crucial there, but it wasn't crucial at the other points. And I guess, can we go back up? Did you had the picture of the sign of the sawtooth function, right? Later on you
drew it again.
Yeah. So like away, and I guess like maybe my thought is like away from x equals 0. If we just fix some interval away from x equals 0, then then the function doesn't, like, x equals 0 is kind of a special point for this guy. Okay. All right, very cool. So symmetry breaking like this, maybe we can cause some problems at cause problems, but at a point. But not necessarily is going to cause problems like everywhere. Does that make sense?
I had a question.
Yeah.
Why does so you said assume that it was the Fourier series of f tilde, but isn't it true that there are Riemann integrable functions that aren't bounded? Like 1 over square root of x is Riemann integrable.
Can I jump in, Christina?
Yeah.
Let's just say this is not. Let's change the sentence before to, because this is I think this is more matter of semantics. Let's just say this is no longer the Fourier series of a bounded Riemann integrable function. And like I think in the book, Stein makes sure to say like his Riemann integrable functions are those that are bounded.
Okay.
So like like 1 over square root of x is unbounded at the origin, and you can make sense of the improper integral as you let x go to 0. But it's hard to make sense of that one with like on each side like if you had to like, does that, you know what I mean? You can make sense of the improper integral on one side,
right?
But then if you had like 2 of them, what do you do? Like,
right. Okay.
So I think like So yeah.
Thank you.
Yeah. Okay, so let's pick up any other questions for Christina. Okay, so let's pick up where Christina left off and use this example of symmetry breaking to create a Fourier series, a continuous function with divergent Fourier series. So the catch is we're going to have to play around with this a bunch, because as like Christina was showing, like we can break this being a Fourier series of an integral function by just chopping off, like just setting like half of the Fourier coefficients, or 1/2 of the Fourier coefficients equal to 0. But it's no longer clear like what we did to the function itself by doing that. But we can but the point is we're going to try to mimic this example with some continuous functions. Okay, so can I share my screen now? I guess I can.
Yeah, I can.
I think I can stop. I think I can just do it from mine.
Okay, great.
I'm the host. Okay. Thank you again, Christina. That was excellent. And thanks, Andy, for the technical assist. Okay, so let's so here's the proposition. There's a Fourier continuous function with divergent Fourier series, and let's do the proof, or this construction. So this is a major caveat is this is something that I forget how to do every time every year. Maybe less than a year. Like I'll have forgotten in a couple weeks how to do this. But like I remember this thing about the sawtooth function symmetry breaking. But in general, this is kind of a tricky. The whole execution is kind of tricky. Maybe the one thing to keep in mind is just the principles of how to go about it, or try to get the idea of what we're doing. Okay, so we'll want maybe that's the wrong way to start. So for every n bigger than or equal to 1, I'm going to define 2 functions. Fn theta is equal to so these are going to be both trig polynomials. This one is symmetric, 1 less than or equal to absolute n less than or equal to n, e to the I n theta divided by n, and Fn twiddle theta, which is what Christina just showed us, to accept the partial sum version of that. So n sum over n equals minus n to n equals -1 of e to the in theta over n. So our intuition from the example that Christina just showed, if I had this infinite sum, is that this guy is going to be poorly behaved. It's not going to have good large n behavior at the point theta equals 0. And on the other hand, since this one looks like the partial sums of the sawtooth function, we expect this guy to be very nicely behaved, in particular to kind of yield something bounded in n, a bounded function. Okay, and this is so this is our claim. Part I is that this f twiddle in the whole the twiddle are going to not be good, and we want a continuous function at the end, so we're going to have to use both somehow. This is bigger than or equal to a constant times log n, some constant times log n. So at 0. So if I look at this function at 0, it grows like log n. And 2, that f in theta is uniformly bounded. In theta. So I take the sup over all n sup over theta, and this is bounded by this is bounded. All right, so the proof of I is I'm just going to plug in 0 to fn twiddle. So, well, what's this equal to? This is equal to the sum from -n to -1 of 1 over n. And you should think this is like log, right? So this is bigger than or equal to the sum from maybe I'll put absolute values around this. Put absolute values around it and just take the minus sign out. So 1 to n, just like Christina did before. N equals 1 to n minus 1. Chop off the last one. N plus 1 dx over x. So as I compare with the function 1 over x, so at 1 over n, and here's 1 over n plus 1. No, sorry. Wrong order. And it's just that this square is bigger than or equal to the rectangle, the size of the rectangle, the size of the integral underneath. This is the so-called integral test, and this is bigger than or equal to up to constants, maybe the integral from 1 to n of dx over x, which is log n. So possibly put some constants in there. Okay, so that proves 1. The proof of 2 is we'll need a technical lemma, namely something like the Tauberian lemma that we proved in homework last week. In particular, the one that Andy did in office hours, I think last week, if I remember correctly. So a lemma to prove 2. So let's let Cn be a sequence with abo means AR sum from n equals 1 to infinity, r to the n, Cn. Suppose AR, sorry. So suppose these are uniformly bounded as r tends to 1. There exists such an n. So this is saying that this is an Abel summable series. If I know some more about Cn, namely that the Cn's are big O of 1 over n, if the Cn is big O of 1 over n, then Sn sum from n equals 1 to n are bound of the Cn's are bounded. So if I'm Abel summable, and if I know some estimate for the Cn's, namely that they decay no slower than 1 over n, then the partial sums of the original series form a bounded sequence. This is bounded because maybe the Cn's aren't are not all positive. Okay, so how do we prove this lemma? Proof of lemma. Well, it's very similar to the proof given in homework. So let R is equal to, how am I doing on time? Let R is equal to 1 minus over n. And then choose, so this tends to 1, as in goes to infinity. And then let me actually skip this proof. It is in the book, and then argue as in homework. So it's actually the identical proof that was almost as the one from the homework last week. So see the book. But that's basically the main idea. And then you're going to split the sum into various pieces, and depending on where this bound is useful. So the idea is to compare the difference. So compare ARs with SNs, and try and show that their difference is bounded, which since the ARs are bounded would mean that by the triangle inequality that the SNs are bounded too. Okay, so Andy gave this proof, this basically the same proof in office hours last week, and it was in it was one of your homework problems. So it's nearly identical argument. Okay, so how does this lemma apply to show that these guys are uniformly bounded? So apply lemma to e to the I in theta and minus e to the negative I in theta over n. And then Cn is equal to O of 1 over n. Okay. And then, so apply lemma to this and note that it's Abel means. So the Abel means are F convolved with PR, which is uniformly, this is exactly the same as Christina's argument that she gave before about the sawtooth function. So these are uniformly bounded. Sorry, this should be F and. Okay. So this means that F and theta is uniformly bounded. Okay, so that's nice. And now comes the symmetry breaking. We're going to start taking this f and theta, and we're going to take f12 and theta, and we're going to shift them. We're going to just shift their Fourier coefficients. In fact, so how do we shift their Fourier coefficients? So the idea, I'm going to displace the centers symmetry on the Fourier side. So I'll set Pn theta to be e to the I to theta, which is equal to the sum times 1 over n, and Pn twiddle theta e to the I 2n theta fn twiddle theta, which is, just as a reminder, sum from minus n to minus 1 e to the I n plus 2n theta times 1 over n. Okay, so where do these functions have non-zero Fourier coefficients? Well, so Pn. So what did I do? So so the Fourier coefficients of Fn lived here, and then I just shifted them all by 2n. So here is 0. So these are the Fourier coefficients of Fn, and then I shifted add 2n to each of these numbers. I get an interval from n to 3n. So here's the domain of the non-zero Fourier coefficients for Pn. So Pn has non-zero only. So maybe I'll write this like this. P n hat k is not equal to 0 only if, or if and only if, and if k is between capital N and 3n. And same for Pn theta, Pn hat k. Its Fourier coefficients are not 0 only if, well, where did the shift happen? These were supported before in this interval from minus n to 0, and then they got now shifted by 2n. So they have Fourier support between n and 2n minus 1, I guess. So only if n is less than or equal to k, which is less than or equal to 2n minus 1. All right, so that's the this is the, so I've taken these two functions and now I've just shifted them, and now their Fourier supports are shifted, meaning the Fourier support being the region where the function has non-zero Fourier coefficients. Okay, so what are the properties? Let me now look at their partial sums. So I'm going to build my function out of these functions. I'm going to build my continuous function out of these Pn thetas, which are just trigonometric polynomials, right? So these are all nice continuous functions. They're both trig polynomials. So what's the game? So the lemma is that, so let's let Pn be as above. Let me update these Dropbox notes. Then let me look at the partial sums, the partial Fourier sums. This is equal to, the claim is that this is equal to, the partial Fourier sum of this function is just equal to Pn if m is very big. Right, if m is very big, then this is a trig polynomial supported on between that has coefficients between n and 3n, and so if I take m be big enough, I just recover back the function back again. I just recover my trig polynomial. But if I take a smaller m, then some things get messy. So the claim is it's equal to Pn twiddle of theta if m is exactly equal to 2n, and it's equal to 0 if m is less than n. Right, so, and this is, let me just draw the picture here. This function is a Pn theta is a trig polynomial, and it only has Fourier coefficients between n and 3n, right here. And so if I take its nth partial sum, and I look at all the, so it means I look at the Fourier coefficients on a bigger interval than this, than the interval of size 3n about the origin, then I get the function back. And something funny happens if I stop at exactly n equals 2n. Then I just get these, right? But that's exactly this function, Pn twiddle. This has so Pn twiddle has Fourier coefficients only exactly in this interval. So right in here. So what's where, remember, Sm is the sum from k equals minus m to m of p and hat k e to the I. Okay, so what's the idea? What's the point here? Is that this these p and thetas are Fourier are trig polynomials that that have the symmetry breaking property only at m equals 2n, and then otherwise they're very benign. I just get back the p and thetas again. So what's the point? If m equals 2n, Sm breaks the symmetry of Pn. Just taking the partial sum where m is less than 2n, I just chop off a bunch of the, I chop off the right half of the Fourier coefficients. And so that's breaking the symmetry of this function. But if m is bigger than 3n or m is less than n, then SMPN is either equals 0 or equals Pn, which are both benign. Right, the 0 function is fine, and the PNs were nice fine functions before, as we saw in our first claim. It's just a shifted. I just took the function, the good functions Fn, and shifted their Fourier support. Okay, so now I'm going to try and build. I'm still not done yet, right? Because I have to. trying to build up my continuous function with divergent Fourier series, nothing's wrong with any of the, I'm just looking at now the partial Fourier sums of these functions Pn. But nothing's wrong with them. So what I want is okay, I guess maybe what I want to say is I'm not going to get anywhere with a finite number of these. I'm going to have to take some infinite sum of these guys, and what I'll do is this is a kind of nasty trick where I'm going to take a sparse sampling of these guys and weight them against a very sparse sampling of them, weighted with a nice convergence series. So choose sequences. Alpha k and nk, such that one alpha k's converges. 2 nk plus 1 is bigger than 3 nk. So this is just, this means it's sparse. You should think of the nks as growing exponentially. I'll give an explicit example in a second. Sparse and exponentially growing. And 3 alpha k. So the nks are natural numbers, and alpha k times log nk tend to infinity as k goes to infinity. So even though the alpha k's are convergent and tending to 0, the nks are growing a lot faster than the alpha k's are going to 0. So example, alpha k just take to be 1 over k squared. So it's some like polynomial type bound for them, and nks to be an exponential, 3 to the 2 to the k, say. So something really really exploding fast. So after taking log of the nks, I still get something growing exponentially. So after I take log of nk, I just get something like 2 to the k, which grows really fast. Okay, now set f of theta, this is my function, to be the sum from k equals 1 to infinity of alpha k times p nk theta. So this is so I claim this is a continuous function. So observe, so the p nk of theta, these are equal just to e to the 2n I theta times f n theta, bounded by the fn theta. So these are bounded by some constant m, right? Because by the first claim we did, that the fn thetas are uniformly bounded in n and theta. So to get the pn's, I just shifted them. So which in absolute value, just multiplying by something of length, a vector of length 1. So these are still uniformly bounded. But then since the alpha k's are for themselves coming from a convergent series, I could just put absolute values inside this integral. Say alpha k's are positive numbers. Say, for example, like think of the alpha k's as 1 over k squared. Let's just take them to be this for the purpose of this construction. This is just, if I put absolute values inside the integral, this is just 1 over k squared. So this series is uniformly convergent, right, on the torus, or on the convergent. So that means that and each of the finite sums is just a trig polynomial, right? So so that means that f is a continuous function. Series converges absolutely uniformly, which implies that f is continuous. Okay. So now, however, if I look at S2n2nm, however, we claim that if I look at the if I pick m, just pick an integer m, and pick the mth, the 2nm partial sum, and evaluate it at 0, I claim this is bigger than or equal to a constant times alpha m log nm plus a bounded function. So this is the claim we're going to prove, and then this shows us that I have divergent Fourier series, right? Because this is just a partial Fourier sum evaluated at a point, and log diverges. It's bigger than or equal to an absolute value than log alpha m times log of m, and I've cooked up alpha n and nm so that this tends to infinity as m tends to infinity. Right. This is how I chose the sequence. This property here. All right. So what? How do we prove this claim? So this is a little technical. So the proof is that S2nm f of theta. What's this equal to? This is equal to the sum from L equals minus 2nm to 2nm of sum from k equals 1 to infinity, alpha k p and k hat of L e to the il theta. Il theta. This is just a definition of the 2mth partial Fourier sum. And to compute this, right, you just, it's a nicely convergent series, so I can just take, so I integrate to find the Fourier coefficients, I just integrate term by term here. Integrate term by term, so I get p hat nk theta, or L, rather. Now, if I plug in 0, so this means that S2, this is the sum from L equals minus 2 and m to 2 and m. The sum from k equals 1 to infinity, alpha k, b n k hat L e to the I. This is just, and then just nothing here, just 1. Okay, so what's going on here? So I'm going to break this sum into 3 pieces. So this, on the one hand, is just equal to alpha m times, I'm going to break the inner sum into 3 pieces. The sum from L is equal to minus 2nm to 2nm of p nm hat L plus the sum from L equals minus 2nm to 2nm. The sum from k equals 1 to m alpha k. And then plus the sum from L equals minus 2nm to 2nm. The sum from k bigger than m of alpha k, p hat, n k, no. Okay, to see if anyone is still sort of with me, which I doubt. This is something where you need to go back and try on your own. What is this? What does this sum give me?
Is it 0 because all the p hats are 0 when k is really big?
Yeah, exactly. So L is small compared to the NKs, right? So L, this is equal to 0 since L is less than 2 nm, and P NK of L supported in NK to 3 NK. Right, its Fourier support is to the right. So k is bigger than this, and this is why I had this sparsity in my sequence, so I can just miss. This last p is just completely 0. So this is why, as long as k is strictly bigger than m, this guy just misses this. This is just this guy is supported only in here, and if L is too small, then I just miss that interval completely, right? Okay, so that's 0. This first part looks good, right? Because this has let me so what happens here if so I claim that this last one here just collapses, right? This first term just collapses unless I have did I write this right? Or sorry, what am I saying? This is exactly, this is, so I got myself confused. This is exactly the 2nm Fourier sum, the thing that we studied before. So this is exactly equal to alpha m times S2nm of P and M at 0. And then plus this rest term, L equals minus 2nm to 2nm. The sum from k equals 1 to n minus 1 alpha k. Okay, and so then this is equal to alpha m times p and m twiddle of 0, which was sorry, let me just do this piece by piece. So this piece is equal to this, which is equal to, which is what we showed before. This was bigger than or equal to alpha m times constant times log nm. And because of the f twiddles, right? The f twiddles have satisfied this pointwise bound. And this other piece here, what's here? We claim this is just O of 1. This is just a bounded term, bounded by a constant. since k less than m, we just get the sum from k equals 1, m minus 1, alpha k, Sn m of p n k of 0, which is just equal to p n k of 0, which are, these guys are uniformly bounded. These are uniformly bounded, and then the alpha k's are form a bounded sequence. So we just get I can put absolute values around inside. This is just something these are just bounded by a constant in n, right? And this is just now so I can bound this by a constant time this sum from k equals 1 to minus 1 case. And since the alpha k's are isolated k, this just gives me a number. So that's it. This proves, this finishes the proof of this bound here. So what does this mean? This means that Sn, we don't have convergence here. The partial sums don't converge. In particular, this guys diverge. A continuous function with divergent Fourier series. Are there any questions? This is a very non-obvious where this comes from argument, and some of these things at the end. This trick is that's clever stuff. But maybe I just say that the idea, like, so Christina gave us the idea that there are some problems with symmetry breaking, and then, like, you can imagine sitting there for 6 months and slowly building this example by trial and error, kind of. Eventually, it's I think just a technical argument from that deep idea that there's some issue with breaking symmetry in the Fourier coefficients. Any questions? And my last point is that, like, something like this would have been very non-obvious to Fourier, right?
I have a question, but it's a little bit more general than like something specific to the proof.
Yeah, that's fine.
So just, I guess, a couple times in this proof and others, we've used term-by-term integration and differentiation. Could you overview of like when that's allowed? Because I feel like it's not always like appropriate to use.
Yeah. So if you have something that's so if you have like absolute uniform convergence, then you can do things like this. So every time we've done it, we've had something that's converging absolutely uniformly.
Okay.
And so if you want to look up, so I attached a file in Canvas with a PDF of a real analysis textbook, and they'll have some, like, if you just look up the chapter on like power series, you'll see when you can differentiate integrate term by term.
Sure.
But I guess the point is that if you have absolute convergence, absolute and uniform convergence, then you can do it. Yeah. If everything's, it's like one, we'll, and maybe my last, maybe what I'll say is we're going to study this in detail in the next segment again. But for now, like absolutely uniformly convergent is enough. Yeah, and maybe the right place to look is like is in the chapter where it talks about convergence of function, like sequences and sequences of functions. And then you're going to want to ask properties of the sequences of functions, where this, if it's a series, then you want to take the nth partial sum, and then the next element of the sequence is the n plus 1th partial sum. And then each of those you can differentiate term by term, the finite ones. So if you have, if there's a theorem that says like particular, if you have a function, if you have a sequence of functions converging uniformly to converging, and the derivatives converge uniformly, then the thing that derivatives converge to is the derivative of the limiting function itself.
Oh, so you can use like the fact you can look at the derivative and just see if it converges uniformly to that.
Yeah.
Then you know, kind of like post hoc, it was legitimate.
Yeah. Yeah. Okay. Yeah. So take the derivative of term by, take the derivative term by term, see if you get something uniformly convergent, and then you're good.
Okay.
Yeah. Maybe it's better than just pointing in a direction. That's the way you prove it. Any other questions? I guess we should go. I'm gonna have my office hours at 4, so I'll hang up to chat, and we'll have office hours, and there's gonna be another presentation in office hours too. Just one today. Okay. See you guys next time.
Thank you.
Thanks.
Great job, Christian.